Welcome, everyone. It's good to see you all. It's been such a good RLDM. It's been a real fun meeting. I've enjoyed it. Yeah, let's give a hand to those guys. And this workshop, I'm excited about it too. Time is so important. There used to be a joke about me, because NIPS would happen, and at the end of every talk, or so it seemed to other people, I would get up and ask a question and say, well, what about time? Because they do supervised learning, there's no time, there's just get examples and do stuff or whatever. I would every time I would think hard about what was missing here, and then it would always be time. And so everyone, they said, Rich is going to come and ask the time question again. And yeah, that was the rumor. So time is really important. I want to start with this common model, which means it's a model that's common in many fields, and maybe it can be common to us. It's not true bias towards reinforcement learning, I don't think, although that's one of the fields that is trying to be incorporated. And like I think we can gladly welcome, say, Josh Tenbaum to talk in these terms, or Jan LeCun. They all want to. I think we all want to have these four pieces inside our mind. It's inside our model of the mind. The perception gets a state representation. We're going to talk about how that involves time, and that, of course, maps to action and also to value. And then there's the transition model, where all the knowledge of the world should be temporal as well. Now, think for a moment now, not about what's inside the agent, but the frame with which it's living within. When it's embedded in time. Every time step, and a time step is like 1/100th of a second. Every time step, a new data comes in, a new observation comes in, a new action must be generated. A new state representation must be generated so that you can apply the policy to it. And of course, reward. Everything's going continually, absolutely continually. And this matters. A lot of times we like to think it doesn't matter. We can just save up our data and we'll process it when we need it. But no, we're embedded in time. We have to make decisions quickly. Computational costs matter. We have to be able to respond quickly. So you notice that I'm calling policies, lately I'm calling them reactive policies, just to emphasize that they have to be some pre-computed thing you can quickly apply to the new situation and decide what to do. So this is the frame with which we're in. And time is central to the operation, as I've just discussed the main elements of that. But I want you to notice that there's this problem I call the problem of the big and the small, and that is the mind has to operate at the small time scale, but the things it has to think about and things it has to produce and deal with are really longer time scales. Like, just the obvious one, reward, you don't really care about the next reward. You care about the return, the discounted sum of the future long-term reward. And so you've got to predict that. The value function is predicting this long-term thing. It's predicting from these microscopic moment-by-moment events. So that's the problem of the big and the small, or the problem of the short and the long. All the important knowledge is long, but you have to learn it one tiny step at a time. And you can see that even in our most basic algorithms, like linear TD lambda, which I will be talking about. Okay, so one further thing you might say is that what we learn is actually a compression of time. So like a value function says now, right away, what's going to happen over the long-term future. So it brings that future into the present. Also, your model about how the world changes, long-term model, you say, if I start behaving this way, these things will happen. If I walk out here, I can get back to the dorms, and it would take me a while, but I'd be there. And that is compressed into my prediction that I could do that, and I could get there, and I could think about that immediately. So in these useful models, the later outcome that we're predicting is a later thing. Even the policy is a compression of that, because it's saying what we should do now in order to get a long-term outcome. Okay, so this talk, I'm going to try to do make 4 points. And there's 2 of them are about model-free reinforcement learning. 2 of them are about model-based reinforcement learning. And of the 2, within each of the 2, the first step is kind of more basic, and maybe you all will know it. And then the second step goes a little bit farther. Okay, but I think it's good to do a mix of both basic things and a little bit newer things for this meeting. Because this is, I took that slide out, but I had a point where we're still figuring out what is in this subject, the subject of temporal representations. It's a new way of thinking, and we're deciding what is the foundations of it. So I'm maybe offering some of the foundations, but no claim really to be all-inclusive, exhaustive. Okay, so let's go on to the first point, the model-free case. I want to talk about stimulus traces. Well, stimulus, maybe we know stimulus is some event that a psychologist will identify in the environment, and then we might have a trace of it internally. So this is that transition called perception, which maps from the observations, external things, to the internal representation of where the agent is. And so this is perhaps the simplest instance of that, where like the outside, yeah, so these kind of diagrams, we use these a lot in psychology. This is just, this axis is time. And so at some point in time, the external representation, like the light comes on for the animal, and then it stays on for some period of time, and then comes off. Now, that's not necessarily how it's represented inside the animal. Maybe the animal is really sensitive to the onset. And so what this suggests is that the light comes on and the representation side maybe grows for a while and then it fades away, and maybe it actually ignores when the turning off event, or maybe there's a separate representation for the turning off. The classic traces are exponential moving averages. So here X would be the external stimulus, and X bar is the trace. It goes up when the stimulus is present and fades when it's absent. Here's some that are clearly onset traces. They ignore the offset of the stimulus events. And here, this is what often happens with a eligibility trace, which is this trace marks essentially this stimulus as being eligible for learning should an important event like a US or reinforcer occur. And then the overlap of the trace, this overlap here and the reinforcer maybe is important for learning. And so I want you to also pay attention to this gap. This is the gap between the two stimuli. And so, by the time the second stimulus happens, the first stimulus is gone, and the trace can help cross the gap. Okay, so this is just getting your mind in the space of possibilities, thinking about all that a trace might be. It might be useful for learning. It might be useful for more than learning. It might be useful for performance. So, the linear TD lambda algorithm, one of our most basic reinforcement learning algorithms, it also exists as a model, a theory of animal learning, classical conditioning, Pavlovian conditioning. And so I'm going to talk about some work that Elliot and Jim Kehoe and I did on the linear model. And so that model, we start with the stimuli that look like these time traces. And then there's this representational process where we come up with a more useful temporal representation. And this, I'm going to bring in the word microstimuli. So if the stimulus is like this, it might give rise to a sequence of microstimuli that gets spaced out over time. Another way of doing it would be just have a train of discrete clock-like pulses. And then you would like to generate a prediction of the US, which would be the second stimulus. And maybe that prediction would have a form like this, and your TD error would have a form like that. And so the model eventually produces a prediction and a TD error, which might be compared to dopamine. Okay, so that's just getting us warming us up. Now let's go through a particular example, because I think this is useful to get our mind behind the algorithm. So the algorithm is expressed by these three equations, and this is a simple example. So this is called delay conditioning, and that means that the stimulus comes on and then it stays on right up until the reward or the US arrives. Okay, so, and then this is a trace of the stimulus. It's something that comes on after this, when the stimulus comes on, arises and then fades away slowly after the stimulus departs. So that's an eligibility trace. And learning, okay, so now I have to bring in my equations. I guess we might start with this one, the prediction. The prediction is just linear in the weights and the stimuli. There's only one stimulus in this example. So so there's one weight, and that weight starts out 0. So you notice on the first trial, the prediction is always 0 because the weights are always 0. and the temporal difference error is the sum of the reward and the change in the prediction. So let's just work it out here. What's the temporal? We can figure it out. The prediction never changes during the trial, so that's not involved. And so the TD error will just be equal to the reward. Okay, and now we're going to want to get learning. Learning happens when simultaneous TD error and eligibility trace. Well, the TD error is always 0, except at this moment in time. At that moment in time, we look at the eligibility trace. It's nice and high, so there'll be strong positive learning. The weight will go up. And so on the next trial or some trial later, I guess this is marked as the very next trial. Now, damn it, keeps advancing on me automatically. In the very next trial, now the prediction becomes non-zero in the presence of the stimulus. Remember, the prediction is the product of the stimulus and the weights. The weight is now non-zero. So the prediction ends up looking a lot like the stimulus itself, just shorter because the weight has just started to increase. Prediction looks like that. So what will the TD error look like? Well, now the TD error, remember, is the reward plus the change in the prediction. The reward is just as it always was. It's unchanged. The change in the prediction now has a positive blip at onset. So that's what we see as positive TD error. And then there's a negative change at the offset. And that adds to the reward, makes so this TD error is slightly smaller than it used to be. It's working its way down. So the weight goes up. So how are we going to have learning? Well, how do we do learning? We look for a simultaneous occurrence of the TD error and the eligibility trace. Well, this first non-zero TD error happens when the trace is 0. That has no effect at all. The second TD error is still happening at the time of high eligibility. So we will continue to increase the weight. It'll increase slightly less rapidly because this one is slightly shorter than the old TD error. But we'll keep going. The weight will get bigger. The predictions will get bigger. Now the first blip will be larger and the last blip will be smaller. So learning will continue, but even more slowly, until finally the positive blip is fully as big as the original reward, and the negative change will be equal, except negative, to the reward. And so the result will be 0 TD error. And at that point, it's not, learning stops because there's no more TD error that overlaps with the eligibility trace. Okay, so that's how it works. And so immediately you can see if I add another stimulus that's just like this stimulus at the same time course, at this point, after we've already learned this first one, if I add a second stimulus that's exactly the same, it would have the same eligibility trace. Would it learn? How much would it learn? Would it learn positively? Would it learn negatively? Excuse me? Won't learn at all because it shares the same TD error and the same eligibility trace, and learning is the product of those two things. So if the first one is stopped, then the second one can't go anywhere either. And so that would be blocking, and it's a major psychological paradigm to show blocking. Okay, so that's delay conditioning. Now, I'm sure some of you have noticed that I'm a little simplifying a little bit. I'm simplifying a little bit when I say the TD error is the reward plus the change in the prediction. Really, there's gamma, there's discounting, and that makes it slightly not true. It would be true as gamma is close to 1. So this is sort of assuming the case where gamma is close to 1. Okay, now trace conditioning, we get a little bit more interesting. Now we have a gap, an interval between the stimulus turns off, and then there's a gap before the US comes, before the reward comes. So as before, eligibility trace comes up, starts to fade. These are going to this reward will have to overlap with the eligibility trace, and its eligibility trace is smaller at this point, but it's still overlapping significantly. And so initially the prediction is 0, initially the TD error is like the reward. It overlaps slightly with the eligibility trace. The weight will increase. You'll get, now notice that the prediction only lasts as long as the stimulus lasts. This is the key observation. Because, you know, our prediction is the wait, time, the stimulus. These are both time series. So although there is a positive prediction, it happens at particular times. And in particular, it's not going to make any non-zero. The prediction here has to be 0 because there are no stimuli at this point in time. So when this thing converges, it will be a sort of mixed state. So it'll be something like this. Prediction will go up and fall. There'll be a positive TDR at the beginning, a negative TDR at the end. Now, which of these align well with the eligibility trace? Well, the eligibility trace is actually quite large here. So it'll like fully see this negative TDR. And this one is positive and larger, but the trace is smaller. So you will stop learning when this is, it'll look something like this. This will be a negative contribution, that will be a positive contribution. They'll balance each other out, and you'll get no further learning at some point like that. Okay, so that's how trace conditioning works. And we're sort of, well, I guess right now we have a prediction, which is that if your stimulus runs right up to the reinforcer, you get a larger learning than you would if there's a gap. Okay, so they've done these experiments. So here are the results of the algorithm. This dotted line is for trace conditioning, is we're plotting how much learning, what does the weight converge to as a function of the time interval, the stimulus reward time interval. So that's the stimulus, it's this in the ISI, interstimulus interval. It's from the onsets of the two stimuli. So if this is positive, you get conditioning. If it's negative, you don't get conditioning. And the best conditioning happens, well, in this paradigm at about 250 milliseconds. And so it goes up and then it goes down. And here we have some animal data from the eye-blink conditioning literature. Actually, this is old, it's from the 60s. Smith and Schneiderman and their colleagues, they also see a similar sort of relationship. And as you're guessing in the delay case, remember delay is where the stimulus lasts up until the reinforcer, then this is a shallower fall off. And if gamma was really 1, you might not expect any fall off at all. Okay, so all that's going well. This is the standard part of the TD model and the temporal representation and the stimulus trace work. And now I want to go towards a little bit of the challenge part, okay? And the challenge part, you should be able to see the flaw that's already present here. If we look at the prediction, the prediction goes up and then it becomes 0, even though, you know, the reward is just about to arrive and our prediction is 0. And we analyze it has to be 0 because this stimulus is 0. And so that's the problem. We can't do what we would like. What would the ideal prediction look like? The ideal prediction would look something like this. It can't become non-zero prior to the stimulus, okay? Maybe that'd be even more ideal. That would be like clairvoyant animal, okay? But if we accept that it can't predict properly before the stimulus arrives, then it should look something like this. I guess I'll admit it. If I can get this. And good. It should look something like this. It should increase. Now I am taking into account the value of gamma. So gamma can never really be 1. And because of that, the ideal prediction doesn't stay flat up to the reinforcer, up to the reward, but it instead should gradually increase along with the powers of gamma. So it should look something like this. Getting feedback from my off my speaker. I have trouble. Good. Okay, so the ideal prediction should look something like that, and notice there's a big difference between what's the actual prediction and the ideal prediction. How can we can't solve that with this setup. We need more. What do we need more? What do we need more? We need memory, or we need some kind of a stimulus trace. We need a trace of the stimulus so that we remember it's just happened. Okay, so the microstimulus, we need some trace of stimulus that acts as a stimulus, as if it was a stimulus. It can't act like an eligibility trace. The eligibility trace doesn't participate in behavior, in performance. It participates in learning, but not behavior, so it can't help us behave. And it's helped us learn, like there was a gap and we still learned, but we still can't perform really well. To do that, we need to add something. Okay, so in the full model, we add these microstimuli. We call them microstimuli. They're just traces or memories of the events. And so this is an example of what it might look like. So you'd have a stimulus event would be a cue, and it would give rise to a whole sequence of microstimuli. And the microstimuli you would expect, the temporal representation, would be things that have just happened would be represented more sharply, and things that have happened a while ago are more diffuse representation. So we see these things spread out as they get farther into the past, really, since the cue happened. And you might also think that the reward also generates a representation, a temporal representation. So yeah, we definitely want to include that. That will generate a sequence, a separate sequence of microstimuli, each of which is really like a full first-class stimulus. It would have its own eligibility trace, and we'll be able to do much more. And so I don't really want to explain exactly how they're generated. They're generated as you might expect, where we have a single trace that, and we then basically code it. We apply radial basis functions to it, or even you could do tile coding, and we generate these stimulus representations that are delayed and more spread out. Okay, and then when you do this, then you can, this is some data from that paper that Elliot and Jim and I did a few years ago. I didn't write down the date or the reference of the time, but we did a lot of good stuff, and you were able then to reproduce the shape of the prediction accurately represents much closer to the accurate representation of the swooping up prediction. Okay, so that's the first half what I wanted to talk about today. I don't know when I started. 15 minutes, perfect. So the other, and I want to talk about the model-based side, unless there's some questions, because it is going to be quite different. If there's something immediate on this, a point of clarification. He said speaking quickly so no one would really raise their hand. Let me push ahead to the model-based setting. So I want to talk about option models and how they enable planning to occur not really simultaneously at all time scales. And then we can even use them for average reward. Okay, so going back to the common model, now I'm going to be talking about this box, what's in the, how this part can be abstract and can take into account long things, not just micro things like, you know, a physics engine, but more like conceptual choices that you could make. You could attend the conference, you could not. Yeah, we want to be more cognitive, have a real transition model that feels like knowledge. Now I have to, this is a slide I'm going to go through slowly a little bit because I want to explain the basic approach to planning in a reinforcement learning context. So planning is, we would think of it as value iteration, which is an old thing from Richard Bellman, 1957. And planning here is use a model of the world to compute the state values. And so let's start with up in the corner, and we have the model. The model takes in a state and an action, and it has two parts, and it produces each of which produces one of the two outputs. One output, the p hat, which is an estimate of the probability transitions for this world. It would give us the probability distribution over the next state, which we might call S prime. Okay, and then we also have to produce the expected reward, an estimate of the expected reward. So that's what R hat is. Those two things, that's constitute a model. And so those are these two things, P hat and R hat. There are these two functions here. They take in a state and action, and produce this expected reward. if you took that action, and it has to produce the probability of seeing S prime if you were to take action A in the state S. Okay, so what it then is value iteration. Value iteration, you just forever, you pick a state, you look forward from it, you guess what, you ask the model what would happen, and then you back it up. So that's suggested before we go to the equation by this picture. This picture is here. We've picked some state S, and we've asked the model R hat and P hat what the reward is likely to be and what the next state is likely to be. Now, what there are two choices we need to make. We need to pick an action, and we need to pick the next state S prime. So, okay, now we can look at the equation. We're going to update the value of the state which we've chosen somehow by taking the max over possible actions, and we say how good that would be in terms of the reward and in terms of the value of the next state that would be according to its probability, summing all the possible next states, the probability of occurring, their values, and then discounting by gamma. And so you just do this over and over again at various states S. And if you keep doing that, if you do it to all the states lots of times, you'll eventually converge actually to the optimal policy given your model. And so that's the way we do planning. It's this weird, it doesn't feel very like, it's like, does it feel like what we go through when we do things? We imagine a state, imagine what we might do, and they say, oh, I could do that, that would be good, that takes the max. I'll do that. And then I stick it in my value function or into my policy. Okay, now time, planning with time, right? The thing that I just showed you was just planning, single step planning. We want to plan with large things. And that seems like it might need something totally different. And the first message is that it doesn't need something totally different. In fact, it's the very same thing will work just as well with abstract actions as with low-level actions. Nothing changes. So we do need a few concepts. First concept is we need this idea of behaving some different way for a period of time. And so that we call an option. An option is a policy and a way of stopping for that policy to stop being applied. So those two things together, stopping a policy and a termination function, those two constitute an option. A special case of options are the primitive actions which stop right away and do some action. And options, we're not going to talk about where they came from, but they can be learned or they can be built in or you can discover them. Now, the option model is separate from the option. The option is this way of behaving. The option model says if you behave that way, what will happen. So you have to describe what state you're brought to and what reward you will have along the way, just like any other model. And so I am gonna, the first point is that if you do option models in this way, they can be used, they're plug compatible with the models of primitive actions and everything just works nicely. The other idea you want to keep in mind is that the ambition here is that the option models are proposed as a general representation of higher level temporally extended knowledge. So we're going to try to keep both those ambitions in place. So maybe this is all can be taken as read, and we just go to the conventional model that we've already seen, and now we're changed it to an option model. I'm showing in red the things that are changed. Okay, so before the input to the model was could only be a primitive action. Now it could be an option. Now it's an option which could be a primitive action, or it could be an extended option, the policy and the termination condition. And the output is now, instead of just being a probability distribution over the very next time steps state, it's a probability distribution over the stopping state of the option, what the state will be when the option says to stop. And then the reward is, instead of being just the one-step reward, it's the sum of all the rewards from the initiation to the stopping of the option. And with those two changes, you have the same equation. This is the same equation you saw before. It's just where the A's for actions are changed to O's for options. Oh, and one other change is there's no gamma here. Once you have an option model, the next states could occur in one step, or they could occur in 10 steps, or they could occur sometimes in 5 and sometimes in 20. They can occur at all kinds of different time steps. And so you can't simply have a factor of anything to correspond to discounting. That has to be mixed into the probability distribution of p hat. And so it's really incorporated in this part rather than separately. Okay. So yeah, I'm down to my last point. I wanted to keep listing them here as we go along in case you want to know what if you understood the main point. The main point that I just did was that option models enable planning simultaneously at all time scales. There's nothing here that looks like hierarchy. There is something here that looks like temporal abstraction, but not really hierarchy. It's sort of flat. Right? I could do this high-level step, or I could do a micro step, or I can intermix them. They're all sort of at the same level, the big things and the small things. And I think that's appealing and elegant. Okay, but I want to do one more step, and this is the thing that's genuinely new, and I should be acknowledging my collaborators, Abhishek Naik and Yiwan, who Abhishek's here. And Easer, they're all in the second row. So how we can get this stuff to where, what is this average reward set? So this slide from a talk I gave in NIP's tutorial where I said we should never have gamma. You know, gamma is just bad. And I want to refine that a little bit. We should never do discounting, which is gamma, if we want to do these other three things. I call this the incompatible quartet. It's incompatible to do all four of these things together. And if you look at the last three, you really want to do those things. So that's why I say you don't want to use discounting. You really want to have genuine function approximation. You really want to do control, not just prediction. And you really want to do the continuing setting because episodes are for children. Episodes are for pedagogy. Like they're really simple to think about, but there are no episodes in life. Life goes on, and when it ends, you don't get to start up again. You know? So there are no episodes in life, and so I think we really are stuck. We have to do all four of these things, and then you can't do discounting. And I'm sure it's not obvious why that's true, but that's the nature of this kind of talk where I'm covering a certain range of things. I have to say things clearly, but I won't have time to explain all of them. But maybe if I say them clearly enough, you'll be able to remember them. We can ask about them and think about them separately if you want to. Okay, so the basics of average reward. First of all, what you're going to, instead of minimizing this discounted sum, you're going to just instead of maximizing the discounted sum, you're going to maximize the reward per step, the reward rate. You want to get reward as fast as you can. It's very natural. And so you have to, it's a little bit tricky to write because it's a limit as time goes to infinity and an average over time steps. It's really the average reward per time step. And so, and the notion of a value function changes. This equation is worth looking at. So now we're going to look at, we're trying to say what's the value. We're defining the value of state S under policy pi, and it's the sum of the rewards that we're going to get if we follow pi, starting from this state at time 0 in state S. And so we're going to sum up the rewards we're going to get, but we're going to compare them to the average reward rate. So this thing is based around 0. On average, it's going to be 0 because our pi is the average reward rate, which is what the rewards are in the long run. So this is based around 0. If it's positive, then that means the state we're looking at is a better state than an average state. If it's negative, then it's a worse state than average. So this is our notion of value. We have the transient, in the near term, are we going to be getting more reward? Well, not in the near term, there's just no discounting, but starting from this state, do you get more reward than average? Okay, and then our approximations, we have to approximate the value functions as usual. We also have to approximate the reward rate. So that's going to be called R bar, which is approximating R pi, our average reward rate. And the algorithms are very simple and very familiar. They use a slightly different TD error. This is the new TD error. It's the change in value with no discounting, just the pure change in value, plus is this reward bigger or smaller than an average reward? And so these are basic learning algorithms. In planning, there's also a similar sort of things. We're going to update this same value function from a model. Here's the equation for that, and I've tried to make it easy for you to consume. I'm showing which things that have changed are shown in red. So this is the original value iteration, and with the discounting parameter in it. And in order to make it average reward value iteration, we take away the discounting. You see it's gone. And we compare the reward to the average reward, the estimated average reward rate. And that's all we have to do. We also have to estimate the average reward rate. But other than that, do rough, it's essentially this. I'll blame my co-authors to say it super carefully, properly in our paper. That's conceptually what's going on. And then to add option models with average reward, well, remember the conventional option model, which we did a few slides back. We estimated the expected reward summing over from start to end of the option. Now we're going to sum the difference between the actual rewards and the average reward. So sort of like, is this excess reward that I get if I did this option? Do I get more than average or less than average? So total sum up from now until stopping. And then with that change, we are unchanged. We just apply the new model, and it's the same value update equation. Now, I think Yi and Abhishek are already probably squirming a little bit because I'm not mentioning something. This is where I'm going to mention that thing, which is that if you look carefully at what I've just proposed, this model is now policy dependent, because R bar depends on, is estimating R pi, which is a policy dependent object. So the average reward depends on your policy. And so that's not happy, because we like to think that our models are just stating things about the world and not stating something about my current policy. So this model is policy dependent, and maybe we want to remove that. I'm not sure we do, but we might want to, and we can. And we can remove it by separately learning. I mean, ultimately it's going to be policy dependent, but we're going to learn it in such a way that the things we learn don't have to be changed as the policy changes. So we're going to learn the expected duration of the option. So I can call that L hat. And the expected summed reward without R bar being subtracted as before. And then the model will actually be our estimate of the actual rewards we're going to get summed up. And then we're going to subtract out the length times the cost per step. So this is going to basically subtract out the R bar after the fact. And by estimating these two things separately, this part will be totally policy independent. This part will be policy dependent, but you know, we're estimating that, and as that changes, we'll immediately incorporate that into the model. And so I refer you to the paper to look at it more carefully. And I think I may be done. Yeah, I've made my 4 points. We need eligibility traces to cross temporal gaps in learning, and we need something like microstimuli to fill the temporal gaps in performance. And in model-based, we want to have models and knowledge of the world that is temporally abstract and is general in time. And option models are a basic tool for doing that. We could get that to work even in the average reward set. So thank you very much.
So we have 10 minutes for questions.
Excellent.
So yeah.
Well, don't start with Dylan. He's my own student. Start with from the back. Oh, yeah, you're. Okay. discount rate, did you say? Discount factor, did you say?
I'm going to say, my personal favorite for this topic, discount. My personal favorite for this topic, discount factor is a particular representation of time. And you're suggesting
Yeah.
that they can-
So thank you, Alan. Let's make this clear. I'm not saying that at all. The discount factor is not part of the agent's representation of time. Even in the normal thought about discount factors, they're part of the problem, not part of the solution.
Right.
So, and I'm recommending that we get rid of them altogether anyway.
But I guess to get to the root of my question, I was wondering whether there are aspects of time that we should learn how to represent rather than embedding in our agents some preconception of, say, options or.
So with options, you are representing your sense of how long it will take well, they do have temporal extent. They last for a while, and they decide when they're terminating, and that's a choice. So the choice of the option is your representation language for expressing the time, and it could be any time. It could be one step. It could be infinite. So we have that flexibility in the option language to represent. Yeah, good. Well, okay, Dylan.
Okay, so years ago, I said to you, Rich, that I think GAN was stupid. Okay, and now I'm going to say that I think that equally spaced time steps are stupid. What do you think about that?
Well, stupid is really kind of strong in both cases.
Intentionally
But
strong.
what we should agree is that the time step should have no real meaning. Like it's a convenience for a notation and for thinking, for us, our thinking. And eligibility traces in some sense free you from the time step, because if like TD0 methods that don't have eligibility traces, they have to do one time step to the next time step, and it's totally important. And like the duration of the time step becomes a big deal. Eligibility traces means you can relax about all that, and you can pick the length of your trace in some real time rather than with respect to this arbitrary time step. So, for example, there are extensions, the linear TD lambda learning algorithm that are totally continuous time, and they don't have any time step at all, and it's the same thing. And these two approximate each other as the time step gets smaller.
We know that like one time step to number in a robot is not going to be exactly the same. Right?
Yeah.
You know, you make milliseconds
Yeah.
off. So should we be incorporating that into our algorithms if we know how much time has passed?
And I was a little. Those two sentences didn't come together to me.
Sure. But if we're doing RL on a robot or something like that,
When you
right?
do RL on a robot, then there are no meaningful time steps, and so we shouldn't be paying attention to time
No,
steps.
that's a clock. Give us an EU clock. Get how much time for that.
In our algorithm we may, but not in the world.
You get a pretty close number.
The world is what it is. We don't know what it is. Yeah. Okay, moving on.
It's going to take off my mask. So you were trying to get rid of the discount factor. What are you doing in terms of the reward function, or what property? Because when you get rid of the discount factor, you're losing your contraction property for the mapping, right? We're going to go through this point. Are you applying some sort of monotonicity?
Okay, so
something that
let's
will
give a little
guarantee conversions?
background on this. To not use a discount factor is not really something that I'm trying to do now, and it's also in the ancient literature of dynamic programming. I think it goes back to 1963 to do average reward dynamic programming. That's fairly well understood, and there's the mathematics of it is different because of the absence of the contraction property due to the discount factor. But there is an applicable mathematics. It's not as easy, okay? But there is a theory for the convergence properties, and that's pretty well understood. course, once you try to incorporate function approximation and the more modern things with machine learning, then there are new challenges.